Hello, everyone. Welcome to the first lab of the Digital Control System course. This first lab is to design and emulate a PI controller for cruise control. I will let you guys read the materials of objective, equipment, and most of the background information. Let us jump right into the main topic. Here's a diagram of the dynamic system of the control target or the plant. This diagram comes from an online control tutorial, and I have listed the reference at the end of the handout. It is a great tutorial, and I encourage you guys to check it out. So in this lab, the task is to apply a force to a vehicle and control the vehicle at a constant speed. By Newton's law, we can develop this first order differential equation. The input is the force U, the output is the velocity V. We can then obtain this transfer function using Laplace transform. In this lab, we further assume that M equal to 1000 and B equal to 50. We will design a PI controller to control the car speed. We will start from analog PI controller. Okay. Here are some design requirements. We require the settling time less than 20 seconds, overshoot percentage less than 10%, and steady state error is 0. This diagram shows a canonical unit feedback control system. Here's the controller, right? The input is error, the output is control effort U. The PI controller in time domain is as follows, right? Showing this equation. There are two components in parallel. The first component is proportional to the error, right? KP here is the proportional gain. The second component is the integration of the error, and Ki is the integral gain. First of all, what is the transfer function of the PI controller? This should be straightforward. You take the Laplace transform and you do some algebra. The next question, what is the transfer function of the closed loop control system, right? You need to go back to this unit feedback control diagram. You reduce the whole thing to one single block. Right? And the output is Y. Y in this case will be the car speed. The input will be reference. All right, in the third step, we will use a PID tuner to design a PI controller to satisfy our requirements. Right? I will show you, give you guys a demo to show you how to use the PID tuner in a second. Right? Basically, after using this PID tuner, you will get the values for Kp and Ki. Once that is done, in step 4, you need to implement the PI controller. You draw the circuit and determine the values for R and C in order to achieve Kp and Ki. All right, so now I'm going to show you how to use the PID tuner. Right, to use the PID tuner, you need first to construct the plant. I mean the transfer function of the plant. Here's a SUML code. Right, we defined or we give values for M, B. Right, so those are the parameters of the vehicle. Now you use the command TF to create the operator S in S domain. Then you just literally type in this transfer function, right? 1 over ms plus b. Then you use the command PID tuner, right? The argument for this command is the plant itself, right? The plant is a transfer function. Right? This command is case sensitive, right? You need to use the capital T. And there are some other options for this command. You can use help to figure that out. You can see, you will see some other options. Okay. For now, I'm not going to worry too much about these options. Once you run this command, the PID tuner will come up, right? So this is the interface of the PID tuner. And there are some drop-down menu from which you can configure the PID tuner. For example, you can import a plant. If somehow you did not give the argument to the PID tuner, you can change the type of controller. You can use P controller, I controller, PID controller, or PI controller. So here, the type is the PI controller, which is what we want. You can change the design this PI controller in time domain or in frequency domain. You can add some plot, for example, body plot, etc. In the middle here, you can see 2 sliding bars. By dragging the 2 sliding bars, we can adjust the parameters of a PI controller and enhance the system response, right? So for example, you can drag this handle, you will see the system response is changing. We will come back to this in a second. Right? We will adjust this so that our requirements can be met. In the main body here, it shows the step response of the closed loop system. And this is not the plant itself. This is the closed loop, the step response of the closed loop control system. By clicking on these show parameters, you can see some important parameters, such as what's the current PI, KP, KI, and KD, etc. You can see the rise time, settling time, overshoot percentage, etc. Okay. So we will use this. So you need to keep this window visible. Now let's come back to the sliding bars. Okay, so there are 2 sliding bars. So in the top bar, we can change the response time. Right? In other words, we can make your system. You can make your system faster or slower by dragging the float handle. Right, just like this. You drag it. You know, if you move it to the right, it will go faster. And there's other ways. For example, you can type in some numbers here, right? You can type in numbers, it will change, or you can use this up or down arrow to tune this to tune the system, become faster or slower. You can also quickly change your system become more faster or slower. So by click on this double arrow, so this will change the system by a factor of 10, right? You can go faster. You can see your system become much faster, right? The settling time is 0.2 seconds, or become slower, just like this, right? When you make change, right, you will see the settling time overshoot the percentage will change. All right, in the bottom here, you can, bottom sliding bar here, you can change the transient behavior of your system. You can make it more robust or more aggressive. Well, in general, when you make your system respond faster, the overshoot may become larger, which may violate your requirement. For example, you know, if you are the current overshoot is about 20%. If you make your system a little faster, so the overshoot will be increased. Now you can change the transient behavior of your system. If you make it more robust, the overshoot will decrease. At the same time, your setting time or read time will increase as well. Just by working on these two sliding bars, you will find a point that all our requirements can be met. Once it's done, you can take a record. You take a note of KP and KI, because we will use that later on. You can export the design, the PID controller. In this case, the PI controller, right? You can name it. By default, the name is C. So now you click OK. You go back to your MATLAB. You will see there's a variable C in the workspace. Now you can show them, right? So this is a continuous PI controller, right? It's a controller object. If you want a transfer function, for example, you want this transfer function, you can use TF command to convert it to a transfer function. Now let's come back to the handout. Now, after using PID tuner, you should have the value for KP and the KI, and you should be able to implement this continuous PI controller using an op-amp circuit, right? Just finding red R's and C's in that circuit. You need to draw that circuit in your library part. Now, the next part is to emulate the design the PI controller using Euler's method, right? The controller we designed is an analog controller, but we don't want to use the analog controller. Rather, we want to use a digital computer for the controller. In other words, we want to write some code, right? And we have learned the advantages of a digital controller in the class. I have created a separate video on emulation. You can check it out. Basically, by using this Euler's method, we will transfer the differential equation to a different equation. Right? Here, you got differential equation by using this approximation Euler's method. In this particular case, is forward rectangular rule. You can turn this differential equation to a different equation. And from there, we can write some code. So I have provided you guys some template. You just fill out some blank in this file. I will go through this file in a separate video as well. Now the last part is to compare the emulation with the continuous system, right? We will do a simulation using the digital controller, which generates the car speed. I already created a simulator for the cruise control. We will do, based on that, we will do some simulation. Right? Then we will compare the simulation with the step response of the continuous closed loop control system. And we want to know how well our digital controller works, right? Once again, I will go through this this MATLAB file, the provided MATLAB file, to give you guys more detailed instruction. At the end, there are some list reference. So this is the website of the control tutorial I mentioned earlier. Right? For your report submission, please submit 2 files. Right? The first file is a report to answer all the questions, to include all the plots or any comments. The second file is the .m file, .m MATLAB file. The code must be executable. Please do not submit a zip file. All right. I think that's pretty much about the handout. Thank you for watching. See you next time.